Okay, good morning everybody. This is section 6.1 dealing with slope fields and Euler's method. We're actually not going to cover Euler today, we're going to focus on slope fields. So to begin, a differential equation. Any equation that has x and y and a derivative of y is what we call differential equation. There's an example. As long as you have a derivative in the equation, it is a differential equation. And when we ask you to solve a differential equation, we are looking for y. What does the y equal to? And when we solve these differential equations, and actually today we're not going to solve many of them, we want to check to see if this equation is a solution to that differential equation. And yeah, I know that's second derivative, but we'll see. This says the second derivative minus the function is equal to 0. So is this a derivative? Is this a solution? Well, we can check by finding the derivative, finding the second derivative, and then we can just check whether this will be true. Get the second derivative, subtract the original function that was given, and does that equal 0? And it looks like this will not be true, so we can just say that no, it is not a solution. And then we could check B and we could check C. On B, given y equal to 4e to negative x, my derivative would be 4e to negative x times a negative, make sure we include the chain rule, which means that our second derivative would be another chain rule is going to happen there to make that a positive 4e to negative x. And we can check whether the second derivative minus the function equal to 0. And given the second derivative that we calculated and the y that was given, it looks like this will be true, and so we can say that yes, in fact, that is a solution to that differential equation. Okay, and I'll let you check C on your own. I believe it's going to be a yes as well. Now, number 2. Given that differential equation xy minus x, we're going to ask you to create a slope field. Now, I know you saw a video on creating a slope field, and so I'm going to ask you to pause the video. I'm going to give you a few minutes, and when you're ready, when you have done enough of these points, you can push play. Okay, so I created a slope field. There it is. And one thing advice that I'll give you when I see that, I did factor out an x. And when I factor out an x, I can tell that whenever the y is 1, the slope will always be 0. So here, whenever the y was a 1, all these had a slope of 0. Now, given that slope field, part B is asking me to sketch 2 different graphs that pass through those points. So let's see, 0, 0. 0, 0 is here. And if I look at the direction of the slopes, it looks like it will be going upward, positive, positive. It'll hit that. But then over here, it'll give me some negative slope. So it looks like it's going to shoot back down this way. At the point negative 1, comma 2, here, I have a negative slope, which tells me that the graph was coming downward. A 0 slope will give me a horizontal tangent and then shoot back up to be a positive slope going up that way. So given the point negative 1, 2, it looks like a parabola, I believe, going upward. And at 0, 0, it looks like a parabola is coming downward. Part C. Can you find the equation of either of the functions that you sketched? And more importantly, how would you find it? Ooh, I zoomed out too much. Well, to calculate that, the answer is yes, you can. And given a dy dx, can we find the solution of y equal? And to do that, we would have to integrate. Now, given an x and a y in the integral we haven't covered yet, we will cover soon, but just know that if you're ever given a derivative, you could always find the solution y. Okay, I'm going to move on. Example number 3, another differential equation. And so I'm going to ask you to graph that solutions, and I will do that fairly quick. I have a 0, 0, 0, 0 slope, a 0 slope, a 0 slope, and a 0 slope. When I calculate the slope at 1, 1, it'll be a negative half. At 2, 1 is a negative 1. This is a negative 2. Now, if that slope is negative 1, that slope right there is negative 2, should be steeper. This is a negative 4, so that one should actually be even steeper than that one. And the same thing is going to happen on this side. This is a positive half. Positive 1, I'm going to make it steeper. A positive 2, even steeper, and a positive 4, even steeper than that. So that should be the slope field that you have. Part B, they're asking me to sketch the graph of the solution through the point 1, 1. Now, let me change colors here. At the point 1, 1. At that point 1, 1, it does have a negative slope. But here is a 0 slope, so let me draw some type of horizontal with a negative slope. So it looks like, oh, we'll have a 0 here. That 0 slope is going to create a function, a solution that looks something like that. Now you could always pause and ask me questions later on. I want to get through the notes, and then we'll address any questions that you have in a few minutes. Moving on. Number 4. There are 3 graphs and 3 equations, and we're asked to match them. So let me fix that a little bit, and let's see. Again, I ask you to pause and pick them out, choose them, and then we'll discuss how we did it. Alright, so if you paused it, let me go in and see what I saw. I'm going to start with that equation. Derivative is equal to 2x. I kind of know some basic stuff about differential equations. I can integrate that real quick in my head. The antiderivative of 2x is x squared plus some constant. See, let's not forget the constant. And so if I know that the equation is x squared, that's a parabola. And looking at the graphs, it looks like this one forms a parabola. Now, whether the parabola is coming through here, or through here, or through here, is all going to depend on the c. But I'm going to call this derivative equal 2x the graph of what? Now, looking at graph number C, I have the derivative equal to y, which means the slope is equal to whatever the y value is. So if the y is 1, the slope is 1. If the y is 2, the slope is 2. If the y is negative 1, then the slope is negative 1. And if I look at what I have left, the slope of the y of 1 has a slope of 1. All these have y equal to 1. And all these have a slope of 1. And when y is negative 1, looks like I have a slope of negative 1. So I'm going to say that this one is for graph number 3, which means this has to be graph number 2. Okay. And I'm going to continue. Right, yet another graph, another slope field. One thing I will do here and point out real quick, when x is 1, this will be 0. So whenever I have x equal to 1, the slope will be a 0. X is 1, slope is 0. X is 1, slope is 0. X is 1, slope is 0. And a few more. When x is 2, I could plop that in and it looks like a slope of 2. And again, when x is 2, slope is 2. When x is a 0, the slope is negative 2. So let me do that. Another negative 2, and negative 2, and negative 2. When x is negative 1, negative 4, negative 4, negative 4. And I hope you could tell that that negative 4 is steeper than that one. And that is steeper than that one, and that is steeper than that one. Okay, so there it is. I did 12, I think, and I'm going to skip the rest. Part B is asking me to sketch the graph of the solution through negative 1, comma 1. So let me go to pencil here. Negative 1, comma 1 is here. So it looks like the graph is coming downward. It does have a 0 slope here, so I'm assuming that it's going to be 0 and then a positive to shoot back up, like that. So there's part B. Next one, part C is asking, does the graph appear to be concave up or concave down? So way back a long time ago, chapter 3, we talked about concavity. Looking at that graph, it looks like it is concave upward. So I'm going to call that concave up. Now, one question that's always asked, why? Justify. How do I know it's concave up? I know that it's concave upward when the second derivative is greater than 0. And so actually, since we have our first derivative, we do have our first derivative. It was given to be 2 parentheses x minus 1. And so, well, let me kind of distribute in the x to make our life easier. If that is our first derivative, we can calculate the second derivative. And the second derivative is the derivative of that, which is 2. Which, and by the way, that is greater than 0. So we can look at the graph and know that it's concave upward. We could actually ask you to find the second derivative, positive 2, and then figure out that it's concave upward. Part D, the next one. Solve the differential equation y equals f of x through that given point. Alright, so let's see. If I am given dy dx to be 2x minus 2, we can ask you to find the y by integrating the derivative. And that is not that bad. What do we get? 2, oops, no we don't. We get x squared minus 2x plus a constant c. I know I haven't forgot it. Now let me go this way because actually I could find that constant c because I'm asked to find the solution at the point negative 1, 1. So at that point, I can find that my constant comes out to be -2. And knowing that my constant is -2 tells me that my solution will be y equal x squared minus 2x minus 2. I could find the solution. I could integrate that. Notice that this only had x's as opposed to the example we had on the first page where we had x's and y's, which we can't do that yet. We will, but not yet. So that is the solution to that differential equation at the point -1, 1. Right? One more piece, asking me to write an equation of the tangent line to the curve at that point again. And then use the tangent line to find the value. The second part is something new we haven't talked about. But the first part we have talked about, the equation of a tangent line. I know a point, -1, 1. It's a point, it was given. I know, well, I could find the slope. The slope comes from the derivative evaluated at the point -1, 1. So I'm going to plug in a -1, 1 into my derivative, which if we did it up there somewhere. We know that the slope at -1, 1, where'd it go? -1, 1, the slope was a -4. So the point is given. The slope we calculated. Remember, you evaluate the derivative at the point, which means that I can write the equation of the tangent line to be that. Remember, do not do anything. That is it. That is the equation of the tangent line. The second part of this question is asking you to use the tangent line to approximate the value of f of 0.1. So asking you to use that to evaluate or to approximate f of 0.1. Well, get that x value, 0.1, and plug it in and figure out what the y is. Like I said, this is something new. It is called linear approximation, which is one of the things that we have not talked about, or we haven't talked about enough, but we'll see what we have here. I'm going to substitute in a 0.1 for the x. A little bit of math. It's not that bad. Okay, I'm almost done. Add 1. And I'm getting -3.4. So what that means is that I was asked to use my tangent line to approximate the value of 0.1. And if I use the tangent line, I'm approximating the value to be -3.4. Now remember, this is an approximation. I could use that point or that equation to find the actual value. Remember, this is the solution at -1, 1. So if I use that, at 0.1, all right, now I'm going to take out my calculator. 0.1 squared minus 2 times 0.1 minus 2. It looks to be -2.19. You could all verify my math. And actually, let me change this. This is an approximation. It's not -3.4. It's actually -2.19. So I went kind of fast. These are the notes for section 6-1. I do want to give you your homework. It is on page 411 from your book, by the way. 5, 17, 23, 27, 43 through 55 odd, and 57 through 60 all. And I don't know what homework number it is, but like always, we'll figure that out afterwards. If you have any questions, let me know. First time I do the notes on YouTube, I went through them fast. You didn't have an opportunity to ask questions through the notes, and that's what the Schoology is for, and remind, and we'll go from there. All right, guys, stay safe.